Hello everybody. So last time we talked about changing your triple integral into spherical or cylindrical coordinates. Now we're going to talk about changing them in general. So hopefully all of you should remember back in Calc 1 or Calc 2, whenever you took it, use substitution, where you instead of doing your integration with respect to x, you're now doing it with respect to u. And hopefully you remember how that ended up working. Well, you can do that with multiple integrals, but back when you were doing single integrals, you changed one variable into one variable. So you can imagine that for this time, instead of changing one variable to one variable, you are actually going to be switching more than one, which means you're going to have UV or UVW substitution, or UVWZ, or whatever. However many variables are within your integral, that's the new types of substitution you'll be dealing with. Now this gets a little bit complicated. So you've seen before when we switch coordinate systems, we have to change our differential up a little bit. So instead of just being dx dy dz, it's r dr d theta dz, or rho squared sine phi d's. Yeah, they get ugly. This is going to talk about where those came from and how we deal with them. So there's a bunch of steps for changing over your systems from one to the other. So if you start with just your basic double integral, the basic premise is the same when you extend it beyond just two variables. So you want to define whatever your new variables are going to be. So define them in some way so it's going to make it more convenient for integration. So you could say u and v equal x plus y and x minus y respectively. Okay, great. So once you have your new variable set up, the next thing you're going to want to do is solve for your initial variables in terms of the new ones. This is a fairly important step. So in this case, x is 1/2 u plus v, and y is 1/2 u minus v. Okay, straightforward now. Here's where the ugly stuff comes in. You have to calculate out the Jacobian. So what the Jacobian is, it's the determinant of the matrices of all of the partial derivatives of your new variables in terms based off your old ones. So for this one, it would be the partial of x with respect to u, the partial of x with respect to v, and then partial of y with respect to u, then partial of y with respect to v, and then you take the determinant of that. You can see how this gets messy. So for this example, calculate out, it comes out to -1/2. Because partial of x with respect to u, well, that's going to be 1/2. With respect to v, 1/2. Y with respect to u, 1/2. Y with respect to v, -1/2. Yeah. Once all that comes out, you get -1/2. All right. Now, this tells you what you're going to have to deal with. So your bounds are going to change, and you're going to have to deal with how that goes around. So you're going to have to know what your region was before and figure out how that deals with your new region. But you now have this set up. So instead of evaluating at x, you switch that up, put in your u and v. But then whatever your Jacobian is, that's what gets put in here. So hopefully by putting in the u and the v, everything goes fine. The simple way is you use this formula here. So by using these formulas, wherever you see an x, replace it with that. Wherever you see y, replace it with that. Put your Jacobian in. This is now not, instead of going to be dx dy, it'll be du dv. And then your bounds are also going to be slightly different. All right. So it works the exact same way for 3, 4, 5 dimensions. So hopefully that helps out, and I'll see you in class.